And I'm really excited to introduce Phil today. Phil is known as the Bad Astronomer, and he earned his PhD in astronomy from the University of Virginia in 1995. During the 1990s, Phil worked on the Cosmic Background Explorer mission, which was COBE, and later was part of the Hubble Space Telescope team at NASA Goddard Space Flight Center, where he worked on the Space Telescope Imaging Spectrograph. In 1993, while working on his dissertation on the rings of debris around supernova 1987A, Dr. Plait harnessed the power of a novel technology called the World Wide Web and began publishing articles aimed at countering one of his pet peeves, the proliferation of inaccurate, wrong, or just plain made-up misinformation about astronomical topics in popular culture. I think this is a timely topic for today. Dr. Plait's internet postings expanded into the Bad Astronomy blog and into his book, Bad Astronomy, Misconceptions and Misuses Revealed from Astrology to the Moon Landing Hoax. Dr. Plait's second book, Death from the Skies, There Are Ways the World Will End, was published in 2008, investigates numerous astronomical phenomena such as black holes and supernovae by charmingly describing hypothetical scenarios in which these events will extinguish all life on Earth. If you're interested in either of these books, they are available for sale out in the hallway through the Boulder bookstore. In addition to his books, Dr. Plait's online and live action work has proliferated in myriad ways as his Bad Astronomer blog has continued at various locations, from Discover Magazine, Slate Magazine, and most recently Sci-Fi Wire. In 2010, he hosted the three-part documentary series Phil Plait's Bad Universe on the Discovery Channel based on concepts from the Death from the Skies book, and in 2015 wrote and presented a 46-episode series of videos about astronomy for the YouTube educational series Crash Course. Dr. Plait has also appeared on many other programs such as NOVA, How the Universe Works on the Science Channel, and The Late Late Show with Craig Ferguson. We're fortunate in that Phil lives in the Boulder area, and when not writing about all things space, he enjoys raising goats, horses, and experiencing the wonderful environment that we all live in out here in the Rocky Mountains. So with that, I'd like to give Phil a warm welcome to Boulder.
Thank you. Thank you. That was, we're out of time. Sorry. Wow, I didn't know I did all that stuff. Yeah, I do live in Boulder. It's really nice, although I'm kind of envying Gaithersburg now because their seats look a lot more comfortable. Look at that. It's like the Regal Theater up here in Longmont. That looks great. You'll be very comfy falling asleep, and they're wondering where I'm, I don't even know if they can see me. They can? Okay. So you have to look over here. If I'm making this pose, yeah, hi. Then there you go. That means I'm looking at you, so stay awake, please. So it is a great pleasure to be here. I visited the National Institute of Standards and Technology when I was, I think, in third grade in Maryland, and I remember some of it, but it was a long time ago. So it's pretty neat to be here again as an invited speaker, especially giving a talk about one of my favorite topics. And I've given talks on people who think the moon landings are fake and that the face on Mars is real, and the Maya predicted the apocalypse in 2012. And it is so nice to talk about a real science topic that has actual data, is a brand new field, and is super, super exciting. Because this is something, when I was a kid, raised as a nerd, and it's also great to talk in front of a crowd of actual, professional nerds. This is great. But as somebody who grew up with Star Trek and all those other great shows, to be able to talk about planets is such a joy. And we had no idea about any of this stuff when I was a kid. It was just all in our imagination, really. And now we are discovering these new worlds and actually starting to figure out a little bit about what they're like, and we can compare them to our own planet. And so that's why I have this talk called Strange New Worlds, because they are these ones that we're finding. But finding these planets, what we call exoplanets, planets orbiting other stars, alien worlds orbiting alien stars. Even though we're doing this because of the love of science, just being able to find these things and learn as much as we can about them. And, you ask any astronomer about that, what they're doing, a planetary scientist, and they'll talk about all that, this joy of discovery and all that. But in the back of their head, right, what are they thinking about? They're wondering if they're going to find planets that can support life. And can there be life like us out there? That's always, even if you're not thinking about it consciously, that question is always floating out there. And so I want to talk about how these planets work, how we find them, what they're like, and then compare them to the Earth. And the question I want the answer to all of this is the Earth special? And it turns out the answer is a little bit difficult to answer. It depends on what you're asking. And so as a true scientist, who hasn't actually published on this, which allows me to say whatever I want, I don't have to worry about the referees, hanging over my shoulder. The answer to this question, is Earth special, is yes, no, maybe. It's complicated. It depends on what you mean when you ask that question. That is a very broad question, is the Earth special? And as you start to drill down into it, you find that the answer completely changes depending on what you're talking about. So, let's start with the Earth. Here's our planet. I love this picture. This is taken from the Discover satellite, which is in orbit around the sun, about 1.5, 1.6 million kilometers toward the sun, faces the Earth, takes a picture every hour, something like that. This was Al Gore's Trieste satellite. Do I have that right? And but it was rescoped, renamed, and it does this amazing job of taking pictures of our changing world. And this is sort of the picture you always see because we are very northern hemisphere and western hemisphere biased, I think. So you tend to see pictures like this of the Earth. You see Africa, Saudi Arabia in there, Mediterranean Sea. This is a very typical view, except it's not. It's the view you see a lot. It might be a stereotypical view, but really, what's a more typical view of the Earth? And that would be this. That hardly looks like Earth. It's not what you're familiar with. There's barely any land visible in there, and I apologize to the people in Gaithersburg that I can't send my laser pointer over the internet, but I'm going to point at a few things. At the bottom left, there's Australia. At the upper right, you can see the west coast of the U.S. There's Baja California and the Sea of Cortez. And that's it. Hawaii is in here someplace, but it's too small and maybe cloudy to see. That's it. That's, as far as land goes, that's all you see. The rest of this is the Pacific Ocean. This is a far more typical view of the Earth, right? 74%, something like that, of the Earth is covered in water. And it's hard to grasp how big the Pacific Ocean is until you've seen it. I've lived in the San Francisco area, and I flew to Australia a few years back, and we left San Francisco Airport, and in 5 minutes we were over the Pacific Ocean, and 12 hours later I was over Australia and did not see a lick of land in that entire time. Basically, the entire hemisphere of the Earth is ocean, and that's kind of staggering when you think about it. It's a lot of water. This is what defines our planet. It's not just that it's a water planet. It's that water exists on the surface in three different states of matter. Liquid, obviously, also gaseous. The clouds you're seeing there are water vapor, so water can exist as a gas. And although you can't really see it too well, at the bottom of this picture is Antarctica, a little sliver of it there below that cloud, and that's water in a solid state. And so this turns out to be relatively important for life on Earth. We need to have a water cycle where water can evaporate, move across someplace where there's not water, and then rain down. And that way life can propagate and exist in different places on the Earth where otherwise it may not be able to. And water is important as far as we know to life. We're carbon-based. All of our biology, all of our chemistry is based on molecular carbon. Carbon is able to create complex molecules that can do all kinds of interesting things, including reproduce themselves. So you can have a long molecule like DNA, and it can replicate itself, and that is sort of the fundamental basis of life on Earth. So water is important. Does that make Earth special? And again, I'm going to answer that in a few different ways here. But let's look at the solar system just as a drawing here. This is a lovely little drawing, not to scale, thank God. It would be very, very unpleasant on Earth. The sizes are to scale. That is the size of the sun and the planets to scale there. And you can see the sun on the left, and Mercury, Venus, and then Earth, Mars, and then a big jump to Jupiter, Saturn, Uranus, and Neptune. So there you have it. All of the planets in the solar system. Every single planet's up there, ending with Neptune. I'm not afraid to dive into controversial politics in this talk, at least passive-aggressively. When you look at these planets, it's pretty easy to categorize them in different ways, and the most obvious one is size, right? You've got the 4 giant outer planets and the 4 smaller rocky terrestrial planets. So if you ask, is Earth special in terms of size, the answer is kinda. You know, half the planets in our solar system are not at all like Earth. Half kind of are. But Mercury's pretty small and rocky and hot. Mars is pretty small and rocky and cold. Venus is sort of the same size as the Earth, but it has this tremendously thick atmosphere, super hot on the surface, rains sulfuric acid there. It's a lot more like Maryland than Boulder, actually. Anybody getting up and leaving on the, no? Okay, good. And so, in the solar system, Earth is kind of unique. As far as we know, we are the only planet that has liquid water on its surface. Now, there are other places that have ice on their surface, including Mercury, which has ice in its poles. There are craters that are deep enough at the poles so that the sunlight never reaches in there. These are called cold traps. And if ice gets in there, it stays there, and possibly for billions of years. So it is possible to have water on the surface of your planet as long as it's in the frozen state. And that's not terribly helpful when we're thinking about Earth-like conditions. So as far as this sort of general overview goes, the Earth is kind of special. We're the only ones that have this sort of conditions on the surface. But is this the only way planets are? Is this it for every planetary system in the galaxy? Well, when I was a kid, we didn't know. We knew, when I was a kid, we knew of 9 planets, and then there were 8 for a while. But it turns out we started discovering other planets around other stars, and that allowed us to do that thing that every 5th grade English teacher likes to teach, and that is compare and contrast, right? As we're finding these other systems, do they look like us or do they not look like us? And what does that mean? And it turns out that once you start to discover these objects, an interesting thing happens, and that you can start to do what I think of as zoology. If you see all these animals in front of you, you want to start categorizing them. It's like this: these have 4 legs, these have 6 legs, these don't have any legs, these swim, these do this, these do that. And when you start to categorize things, you start to learn more about how they interact, how they behave on their own, and maybe how all of these things came to be, up from simple protists up to the complicated life systems that we see now through evolution. Planets don't really evolve like that, but same principle. The more of them you see, the more of them you can figure things out. Is the Earth unique? And that's the question. Let's see if we can find the answer. So first of all, how did we find these planets? It turns out this is really hard. Until suddenly it becomes super easy. When I was a kid, I used to read a lot about efforts to look for planets around nearby stars, Alpha Centauri. For those of you who were big into astronomy like I was, VB8b, Van Manen's planet, all these things. People were looking for these planets orbiting nearby stars using different methods, and they could never quite do it. It's really, really delicate, precise work. And it turns out what you really need are digital detectors. And once you start to put those on the back ends of telescopes, you can start doing a lot more precision measurements. And I'm going to skip, actually, the first method we use to actually find a planet and go straight to the transit method, which is far and away the most successful method. Basically, what you do is you look at a star and stare at it for a long time. And what you hope is that if there's a planet orbiting that star and the orbit of that planet is seen edge on from Earth. So, it's not face on, it's not doing this, but we're seeing it edge on. Then once every orbit, it's going to pass in front of that star. And what will happen is if it does that, you get a mini eclipse, and the starlight drops a little bit. So if you can measure very precisely the brightness of a star every whatever amount of time, every day, every hour, whatever, and you tick, 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 you just keep measuring it. If that planet happens to pass in front of that star, you get a mini eclipse, and you get a little dip in the sunlight, just like this animation. So here's a star, and we're going to plot brightness versus time, and as the planet goes around, right, it blocks the light from that star. And there's a little bit of as the planet goes around the star from our angle, it goes through phases like the moon does. It goes from crescent to full. I can play this again. Sorry, it doesn't loop. Here we go. There it's new, first quarter, full. Oh, well, you only get half of that. There we go. Maybe I did that wrong. Here we go. And so as you do this, the measurements, there's a little bit of noise in the measurements, but overall you see sort of that dip in the light from the star. That is a transit. The amount of information you can glean about a planet from something as simple as this is really quite stunning. If you know how big that star is, and it turns out we can do this, there are very complicated methods to determine exactly how big a star is. As that planet passes in front, if the planet's really big, it's going to block more of that light, so you get a deeper transit. If the planet's smaller, it blocks less of the light, and the transit is shallower. So right away, if you know the size of the star, by how much light is blocked, you can get the size of the planet. Now, you can't necessarily get the mass of the planet. I'll get to that in a moment. But there are other tricks you can do that tell you things like what the orbit of that planet is. The time it takes for it to cross the star tells you how long it takes to orbit the star. And if you know how long it takes to orbit the star, you know how far from the star it is. And that tells you right away sort of kind of how hot the planet is. Now, that depends on a lot of things, if the planet has an atmosphere or not, or a lot of other stuff, but it gives you an idea. It's like if the minimum temperature of this planet is 1,000 degrees, probably not the best place to look for life. On the other hand, if it's in an Earth-like orbit around a sun-like star, that becomes interesting. There are other things you can tell from this as well. I won't go into detail, but you can read about this if you want. But you can learn about the atmosphere of the planet. You can learn a little bit about the star itself. Just a huge amount you can learn from this as long as your measurements are accurate enough. And this is far and away the most popular, so to speak, the most successful way of planet finding that we've got right now. Now, the first way that we found planets, at least, although the story gets complicated, is using what's called reflex velocity or radial velocity. Now, as a planet is orbiting a star, that planet has mass. It has gravity. Not much. I mean, it's orbiting a star, a gigantic, massive object. But the planet still does have some amount of gravity. So as the planet is going around the star, it's tugging on that star. So as the planet makes, let's call it a circle, a big circle around the star is making a little circle as well in the opposite sense. So as this thing's going this way, they're kind of tugging around each other. And you can think of this, if you're standing with somebody who, say, is a kid, somebody who's much smaller than you, face each other, hold hands, and swing that kid around. That kid's going to make a big circle around you, but they're pulling on you as well. So you're going to kind of make a circle around them as well, around your center of mass, right, where you're balancing. Astronomers call that the barycenter because why call it the center of mass, which is obvious. Call it the barycenter and confuse people instead. That's how we like to do things. And so you can see that on the graphic on the left. And so the star is making a little circle. Now that circle typically is way too small to see with a telescope. You can take 1 million measurements of a star and it's not going to look like it's making that circle simply because this system is really far away. It's trillions of kilometers away at least. And that circle it's making is very, very tiny. However, this is the cool part. If the orbit is edge on like it is on the right-hand animation, then what you're doing is, that star you're seeing it moving back and forth. The back and forth isn't the important part. It's that it's moving towards you for half the orbit and moving away from you from the other half of the orbit. And so if you point a telescope at this thing and measure the light from the star extremely carefully, you can see a Doppler shift in its light. This is the same thing you get if you're standing on the road and a motorcycle goes by and it goes, right? The pitch changes. The pitch is higher as it's moving toward you and lower as it's moving away. That's the Doppler shift. The same thing happens with light. An object's moving toward you, the wavelength of the light shrinks, and we call that blue shifting. If it moves away from you, the wavelength increases, and we call that red shifting. It's a very, very small effect because it depends on the velocity of the star. And the star is making this little circle that may take it weeks or months to move around. And so the typical velocity of a star as it's moving in this little circle is like tens or hundreds of meters per second. It's not very much. However, we are really, really good at building telescopes and spectrographs, and you can measure this for a lot of these stars. And the more massive the planet is, and the closer it is to the star, the bigger that effect is. And so, the very first planets that we found were these planets that are very close into their star and very massive, simply because those are the easiest things to find using this method. The joke is it's where the light is better. Cop's walking down the street at night and there's a kid under a street light on his hands and knees. And the cop says, "What are you doing?" And the kid says, "I'm looking for a quarter I lost." And the cop says, "Well, where'd you lose it?" The kid says, "Over there." The cop says, "Why are you looking here?" "Because the light is better." All right. Dumb joke. Yes. However, that's how astronomers think. So, we looked at stars, a bunch of them, and found a lot of planets orbiting stars this way. It turns out these are massive planets, much more massive than Jupiter. And they're orbiting their star extremely close in, such that their orbits are measured in days. Now, Mercury is the closest planet to the sun, and its orbit is 88 days long. And yet we're talking about planets here which are orbiting their star in 4 days, 5 days, something like that. So they're very close in, really yanking on that star hard and making it much easier to see this Doppler shift. So that's why this is called the reflex velocity. The star is moving in reflex to the planet moving around it, and it's the velocity that's important. So finding these hot Jupiters was a big surprise. Nobody was expecting to see these because they don't exist in our solar system. Ding! Aha! Answer to our question right away. Is our solar system unique? No. Or I should say yes. It's not unique in that other solar systems exist. So we are finding planets around other stars. Hooray! So we're not the only planet in solar system in the galaxy. We didn't know. It seems like solar systems are easy to make because ours exists, and there doesn't seem to be anything special about the sun necessarily. Lots of stars like it. But without knowing for sure, we just didn't know. So now we know. Is our solar system unique? No. Other ones exist. Is it unique in its structure? Maybe. We don't have planets like this in our solar system, and yet these were the ones that we were finding lots of at first. Well, we were finding them because they're easy to find. As we got better at this, we started finding lower mass planets farther out from their star. And the beauty of this is that the shift that you see in the star's light depends on the mass of the planet. And suddenly, if you have an edge-on system like this, and it's transiting as well, you now have the size of the planet and you have the mass of the planet. And if you divide basically the size by the mass or the mass by the size, you get the density. And now we have the density. That tells you very much good things about your planet. Look at Jupiter, right? Jupiter's a big planet, but its density is very low. It's only about as dense as water, about 1 gram per cubic centimeter on average. The Earth is about 5.5 grams per cubic centimeter. And look at the Earth. It's got its huge iron core, got a lot of rock, and a very thin atmosphere. Jupiter also has a very large core, but it's mostly atmosphere. That dominates it. So its density is very low. So without even physically seeing this planet, if you can get its mass and its size, you can tell right away, is this thing, a solid terrestrial-like planet, or is it a giant gaseous gas giant? Hope that wasn't a confusing phrase for you. And that's amazing that you can do this. Now, the thing about a transit is that Jupiter, orbiting the sun, Jupiter is about 1/10 of the width of the sun. So you put Jupiter up next to the sun's about 10 times wider. But it's blocking an area, and that goes as the diameter squared. So since Jupiter is 1/10 the size of the sun, it actually blocks 1/100th of the sun's surface when it transits. So that would be a 1% transit. Typically, that's the kind of transits you see with these Jupiter-sized planets around sun-like stars. That's a 1% drop in the light. That's super easy to detect. I have an 8-inch telescope at home that is an off-the-shelf telescope. If I buy an off-the-shelf camera, I could actually point this thing at quite a few of the stars that have these planets and detect them. These were sitting in front of us all this time. It wasn't until we could prove that this happened that this took off. And then NASA launched the Kepler Space Telescope, and then that was a huge boom. Kepler has discovered over 2,000 planets this way. A bunch of ground-based telescopes have discovered lots of planets this way. We now know, between this method, and the transit method, the reflex velocity method, and a handful of others that are less efficient, we now know of almost 4,000 planets orbiting other stars. 4,000. The first one was discovered in 1992. A 3-planet system orbiting a pulsar, a dead star. It's not a sun-like star. Those planets are pretty weird. It's not, it's cool, but it wasn't really what we were looking for. But the first planets orbiting a sun-like star were discovered in 1995. And then it took a couple of more years. We started finding more and more. And now we're finding these things almost every day. It's pretty rare that a new planet isn't added to the roster basically every week. And we're really close to 4,000 of them now. The Kepler mission's over, but now we have TESS, which is the Transiting Exoplanet Survey Satellite. I always have to think about that. And that is, Kepler stared at one spot in space for years, looking at 100 and something thousand stars, looking for planets around them. TESS is a survey instrument. It's sweeping the sky, and it's looking at brighter stars, looking under the assumption that brighter stars tend to be closer to us. So it's looking for nearby planetary systems, and it launched not that long ago, and it's already discovering them hand over fist, although it has neither hands nor fists. But it's finding lots of planets. This is a very exciting time to be into this stuff. There is a third method which I have to talk about because it is so cool. As an amateur astronomer myself and somebody who's always loved looking through telescopes or getting data, optical data from telescopes, it turns out that in some special cases you can see these planets. They're not detected indirectly like these other two methods. In this case, you take a picture and there's a planet there. This is Beta Pictoris, a relatively nearby, very young star. In the middle, there's a little piece here. This is a picture taken in November 2003 in the infrared, and the star itself has been blocked. That star shows you where it is. And there is a planet. That's Beta Pictoris b, Beta Pic b as we call it. Picture taken 6 years later, this is where it was in 2003 at the upper left at about the 11 o'clock position. 6 years later, it's down here at about the 5 o'clock position, something like that. That's because we're seeing it orbiting its star. We're seeing it orbiting its star. I've known about this for, 15 years now, and it still makes the hair in the back of my neck stand up. So cool. The bottom picture shows the two of them together, another picture taken in March of 2010, and you can see it's moved a little bit from its 2009 position. It's basically orbiting the star. We're seeing it almost, but not quite edge on. Very disappointing. It was supposed to transit last year, and it didn't. If it had transited its star, then we'd be able to determine a lot more about it, its size and its density and all that. Unfortunately, we didn't. But you can see there's a picture of Saturn's orbit there for comparison at sort of the same angle, and that's how this planet is moving around a star. And you can see that. This has been done for many other stars. HR 8799 is another great system. Again, the star is in the center and blocked out. And we name the planets in order of discovery. So it's B, C, and D. There's no A for historical reasons. So D is actually closer in, but it wasn't discovered at first because it was harder to detect. B was the first one found, even though it's farther out. A picture taken a little bit later actually shows, 4 of them, but I have an animation of this. This is a bright enough star, easy enough to detect that you can see B, C, D, and E. I can't remember which one is which, but here's one here, very faint, and the 3 brighter ones on the other side. I can play that again. You take enough images, you can string them together and get a movie of the motion of these planets orbiting their star. Love this. That is science fiction, baby. That is Star Trek right there. And that's for real. Now, the reason we can see these planets is that the star and the planets are very young. They're only a few million years old, and that makes them very hot. They're still cooling from their initial formation. and hot things glow in the infrared. And we have detectors that can detect infrared. The star is not nearly as bright in infrared, and that makes the planet look brighter in comparison. A typical planet's a billionth as bright as its star in optical light, but it may only be a millionth as bright in infrared. And that still sounds like a small number, but it's 1,000 times better. And so you can do stuff like this. And that to me is amazing. We've actually directly imaged over a dozen planets this way. Pretty phenomenal stuff. I love it. So, where does this put us as far as uniqueness goes? Well, let's talk about what makes the Earth unique. Exoplanet astronomers and astrobiologists, which is a real thing, that is a real thing that NASA does now. You would have been laughed out of your grant money, I don't know, 20 years ago, 30 years ago, calling yourself an astrobiologist. Now you can get a PhD in it. And there's this concept called the habitable zone. You're probably familiar with this. And that is basically how close or how far you can be from a star such that conditions are temperate. You can have liquid water on the surface of whatever this thing is. This is if I can quote Pirates of the Caribbean, this is more of a guideline than a rule. I see a lot of Michael Bay fans in the audience. Okay. So the idea is that if you're too close to the star, you're too hot and water will boil away. If you're too far away, it's too cold, it'll freeze. And you want to be in that zone that's just right. A lot of people call this the Goldilocks zone. That's what we were calling it for a long time, actually. And then somebody came up with habitable zone, which is actually much harder to pronounce. However, I'm not a big fan of calling it the Goldilocks zone because it should really be called the baby bear zone, right? Goldilocks is the one who walks into this house and says, oh, this porch is too hot. Oh, this porch is too cold. Oh, baby bears is just right, right? And so we should really call this the baby bear zone, but this is very typical, European colonization thinking that, this white girl's going to go into somebody else's cabin, steal all their stuff, and we're going to name it after her. All right, great. And if that gives you a flavor of my politics, congratulations. This is a government facility. I should probably shut up. But I can't. So this idea that you can have this habitable zone is a nice guideline. The reason it's a guideline is because look at our own solar system. Venus and Mars are on the edges of the sun's habitable zone. The Earth's pretty much in the middle, relatively speaking. So Venus is on the inner edge, but it's not habitable because of its atmosphere. It has a lot of carbon dioxide in its atmosphere that traps a lot of heat. And it had a runaway greenhouse effect, and now it's hot enough to melt lead on the surface of Venus, more or less. Very, very hot, completely uninhabitable. Kinda. Maybe I'll get back to that. Mars is very small, has very little atmosphere, and it's very cold. If you could swap Venus and Mars and, wait 1 billion years or something like that, it's entirely possible that Mars would get a thicker atmosphere, Venus might lose some of its atmosphere, and they would be habitable, and we'd have 3 habitable planets in our system. But as it is, they're not. So just because a planet's in the habitable zone doesn't make it habitable, any more than just because a planet is Earth-sized doesn't make it Earth-like. Venus is very close to being Earth-size and mass, but it is an entirely different planet. So you have to be careful about the terminology you use here. Now, this is the habitable zone in our solar system. There are different kinds of stars. There are hotter stars, there are cooler stars. A hotter star has a much larger habitable zone. It's just the way the math works out. And so you can actually, the inner edge is probably farther out, of course, than the inner edge for our habitable zone, because the star itself is hotter. You have to be farther away before it's cool enough. But at that point, you can be much farther out from the star and still be in that habitable zone. As stars get cooler, that habitable zone shrinks and starts to huddle much closer to the star. And when you're talking about M dwarfs, these little dinky red dwarfs, those have a habitable zone that's very close to the star. Do we see planets in the habitable zones of their stars? Right? Is Earth unique in being the only planet sitting right at that great spot in the middle of a star's habitable zone? Does that make the Earth special? And the answer is, oh no. No. We find lots of planets in the habitable zones of their stars. You look at G stars like the sun, that's just the term that astronomers use for stars like the sun. And this is an old plot. This is from a couple of years ago, but it's beautiful the way it's displayed, so I still use it. We have a lot more of these than what's shown here. But Kepler 452b, it is the 452nd star in the catalog that Kepler used it has another name, but as far as the Kepler catalog goes, 452nd star, the Kepler looked at and found a planet around. B makes it the first one discovered around that star, and it is in the habitable zone of Kepler 452. K stars, a little bit cooler than the sun, kind of more orange than the sun is, and we found a bunch of those. And then around red dwarfs, what we call M stars, a bunch of those too. This is an old, like I said, this is an old graphic. We know tons of them. It turns out M stars are really good at making planets that they can orbit around their habitable zone. The interesting thing about this graph is that although the distances are not to scale, the sizes are, right? So we know that the Earth is not unique because there are other stars that have planets in their habitable zone. But now, when you look at this plot, you realize, hey, the Earth's not unique. We're discovering lots of planets that are roughly the same size as the Earth. But do you notice anything about all these planets compared to the Earth? Are you awake? Come on, it's the National Institute of Standards. You guys have to like automatically go, oh, well, if you categorize them, it's a little bit hard to tell from this plot, but they're all bigger than the Earth. By the time you start looking at planets around the size of the Earth, it gets pretty tough to see them. The Earth blocks about 1/10,000th of the sun's light if it were to transit the sun seen from another star. And so now you're talking about 1/100th% drop in the starlight. We can do that, but it's tough. And as planets get smaller, it gets harder to detect them. And so these planets are all bigger than the Earth. And it turns out planets bigger than the Earth, we call them super-Earths. They don't have a cape. That's not the way you can tell. But it turns out, there are a lot of these out there in the sky. Here is this is just a drawing representing some of the super Earths we found, just to give you a size comparison. And you can see Kepler 62 has quite a few planets around it, at least 4 for B, C, D, and E. And these planets are all bigger than Earth. Once they get about twice the width of the Earth, and if they're also dense like the Earth is rock and metal, their gravity gets so strong, we think, that as they form, they're able to draw in more material much more rapidly. And so you get kind of this jump as a planet gets bigger. It's Earth, super Earth. Once it gets about twice as big, suddenly it can grow in size hugely as it's forming, and it becomes more like Neptune. And so planets that get that big, we start to call them mini Neptunes. This is not a hard and fast rule. It's just a guideline to have us understand what we're seeing. So now that we can start to see lots of different kinds of planets, we know that super Earths are out there, how does this stack up? When we start to look at all these planets and we can determine their size, how many of each kind of size are we finding? And it turns out you can plot that. This is one of like 2 plots in this talk, so I apologize if you don't like math. But this is really easy to read. Basically, size goes left to right. Left-hand side of the plot is small, right-hand side is big. Up and down is just how many of them we've seen. So bottom is 0, top is a lot. Doesn't matter what the number is. It's just more. And what you see is Mars-sized planets, you see hardly any. Well, does that mean that there are very few Mars-sized planets out there? No, it means they're really hard to find. The light is not good there, to use that metaphor again. These are tiny planets. They do not affect their star much, whether they're blocking the light or tugging on it. So they're much more difficult to find. We have found a few. We've even found some almost as small as Mercury. I think one of them is about Mercury size. Very marginal detection. But there could be lots of them out there. We're just not finding them. Once you start to get to Earth-sized planets, we're starting to get more complete in our surveys. We're finding lots of those. But then you see a big jump to super-Earths and mini-Neptunes. Far and away, the most planets we're finding are somewhere between the size of Earth and Neptune. And then when you get to Neptune size, there's a sudden drop, and something bigger, something getting closer to Jupiter, there are even fewer. And Jupiter and super Jupiter, we find not that many. And here's the thing. If there's a Jupiter system and it's an edge-on system, yeah, we're going to find it. It's super easy to find. Like I said, I could do this with my backyard telescope. So our surveys are telling us that there really aren't that many Jupiter or super Jupiter planets out there. Stars don't make them as easily as they make these super Earths and mini Neptunes. That's a real effect. So basically, stars make those middle-sized planets really, really well. How many of those do we have in our solar system? Ooh, none. There's none. The most common type of planet maybe in the entire universe, and our solar system doesn't have one. That's interesting. Is that important? Maybe. If we find planet 9, this hypothetical planet orbiting way out past Neptune that's been talked about a lot recently, that may be a super Earth. And so we may have one in our system. But the thing is, if it's that far out, it's almost impossible to detect using any of our methods. So what we're finding here are super Earths that are relatively close into their star, and our solar system doesn't have one. There is an idea that we used to, that there were some super Earths, maybe as many as 5, orbiting the sun between the sun and the orbit of Mercury. They weren't stable. They crashed into each other and basically smashed themselves to pieces. Most of those pieces blew away, but then the debris settled in and formed the 4 inner planets of our solar system. And so we're sort of a second generation planet formed from the debris of the first generation super Earths. But that wouldn't have been possible if we didn't have those super Earths in the first place, and we don't have them now. So not having super Earths is telling you something. We don't know what exactly. Maybe we used to have them, maybe we never did. But right away this is telling you, yeah, our solar system is special in some way, that we don't have these types of planets. That's amazing to me. So we're getting a better handle now on whether the Earth is unique or not. However, are we being too picky? Was Goldilocks too picky? Well, we know Goldilocks was too picky. She's really picky. Let the hot porridge cool for a couple of minutes. Come on, how hard is that to do? But maybe we were being too picky about what we want for conditions for life. Now, Jupiter is a huge gas giant, mostly atmosphere, probably not habitable in the way we think of it. But it has these giant moons. That's Europa there, and that's Io, the volcano moon. Europa is an interesting moon. Here's a close-up shot of it. It's an icy moon. We've known that for a long time. When we got up close to it, it has these cracks in it. And as probes investigated it more, we realized that it actually has a subsurface ocean. Basically, as it orbits Jupiter, the gravity of Jupiter flexes, it compresses and flexes the moon. And that creates a huge amount of friction inside the moon, which warms it up. It's mostly water ice. When you warm up water ice, you get water. So we think there's an ocean under there, and even a core of rocky material, which is very interesting because that means there are minerals there that can interact with the water, and we think that might be salt water, which is possibly how life on Earth originated. The conditions under Europa's surface may be very similar to conditions that existed on Earth when life arose. So you don't need even to be in a habitable zone, maybe, to have life. We know that there's liquid water that exists on these icy moons. And we've seen it, in fact. We didn't see it in Europa, we've inferred it. But this is Enceladus, a moon of Saturn. It has these parallel bluish streaks in this picture at the bottom. This is all ice. Interestingly, it doesn't have very many craters on it. It's a very old moon. If it doesn't have craters on it, that means the surface has probably been repaved sometime recently, hundreds of millions of years ago. That indicates that maybe there's tectonics or some sort of geological process which is pouring liquids over the surface, which then cover up the craters. And you've got these big stripes here. These are actually cracks in the ice, and Cassini discovered that there is water spewing from these things. These are geysers seen backlit by the sun. You can actually see the shadow of the curve of the moon there, and these are geysers shooting out into space. Cassini flew through those geysers and found that there's dust in them and organic molecules. Now, not, life molecules, but carbon-based molecules, which means that the ingredients for life are under the surface of Enceladus. It, too, has a liquid water ocean under the surface. How common is this? And, this was kind of a surprise in the 70s when it was first thought of for Europa, and then the 90s and 2000s with Enceladus. But it turns out this may be very common. This is Rhea. Yes, Rhea, a moon of Saturn. Titania and Oberon, moons of Uranus, I believe. Triton, around Neptune. Eris and Sedna. These are gigantic Pluto, roughly sized objects out past Neptune. All of these objects may have liquid water under their surface for various reasons. So it turns out having liquid water is not a unique property of Earth at all. Even Pluto, this shocked me when we got the close-up pictures of Pluto and you see this heart-shaped feature, Sputnik Planitia, Sputnik Planum. And the western lobe here, the left-hand side of the heart, Tombaugh Regio, is very smooth. And it turns out it's been repaved recently too. I would have thought that Pluto was a frozen ball of rock and ice. And it turns out no, there is still heat in its interior. There is still liquid under its surface. This tells you that this stuff is everywhere. Everywhere. Is there life there? Don't know. I'd love to know. We don't know, but the conditions look interesting. But now wait a minute. Are we talking about liquid or are we talking about water? Because if you need just a liquid of some kind, it turns out there are other types of liquid as well. This is Cassini's shot of Saturn with the moon Titan there silhouetted against it. And when Cassini, Titan has a very thick atmosphere, very thick nitrogen atmosphere that's too thick for optical light to penetrate. But Cassini has radar, and it could beam this radar down to the surface, have it bounce back up, and it could map out the topology, the surface features. And near the North Pole of, I believe it's the North Pole of Titan, this gigantic moon that's basically about as big as Mercury. It's a planet-sized moon. It found these areas that were not reflecting its radar. And the only thing that doesn't reflect radar is liquid. It absorbs it. And so this became very, very interesting. And then as the images got better and better, you started to see that, yeah, this looks like a lake, right? There are tributaries feeding into it. They get bigger and bigger as they get closer. And it turns out, yeah, this is a lake of liquid methane on Titan. And Titan has a methane cycle. This stuff evaporates. It forms methane clouds. They move over to the surface where it's dry. It rains down and then forms these rivers that flow back into the lakes. Can you have life based on methane instead of water? I don't know. Why not? Nature is surprising. Nature knows a lot more about how it works than we do. So it's constantly surprising us. There could very well be some sort of life based on this cycle and not based on water. Now, it's very cold on Titan. Water there is so hard that it's basically like granite. You know, if you made a snowball here on Earth and brought it to Titan, it would turn into rock as hard as at the top of the Rocky Mountains here. You don't want to get in a snowball fight like that. It's just telling you conditions are very different and yet eerily Earth-like. So we're not even unique that we have liquid water on its surface. Is there another way we can look at the Earth? And the answer is yes. Here's Mars. Tons, it's very dry, very cold, very thin atmosphere. Huge evidence, conclusive evidence that it used to have a lot of water on its surface. There are dry lake bed, dry channels of rivers. There's even indications that there was a standing ocean on Mars. That's a little bit controversial, but I'm fairly convinced by it. So 4 billion years ago, something like that, Mars might have looked like this, and it may have had oceans, thicker atmosphere, weather. Mars, 3.5 billion years ago, something like that, was more Earth-like now than Earth was then. Earth then was still too hot. Mars was already like this. And so could life have originated on Mars back then? Absolutely. There is no reason not to think it could have. So we don't know. But it might have. And there's, you've probably heard of panspermia, this idea that life may have started on Mars, giant asteroid hits Mars, blows debris up into space, and it falls to Earth and becomes us eventually. We may be Martians. That is entirely possible. It's unlikely. I think conditions on Earth were fine for life to arise just later than Mars. But the point is, we can't be prejudiced. We can't just look at a habitable zone. We can't just look for liquid water. We can't even just think about now. Planets a long time ago may have been Earth-like a long time ago, even if they aren't now. Are we ready to answer the question I posed at the beginning of this talk? Yeah. And it's the answer I gave you. Spoilers, right? Is Earth special? Yes, no, maybe. It's complicated, right? It depends on what you mean by the question. Are we special in our position in the solar system? No. There are lots of planets in the habitable zone. Are we special in our size? No. A lot of Earth-like planets. Are we special in that we look like other solar systems? Yeah. We don't look like a lot of other solar systems. There are other solar systems that look like us, but they're in the minority. Most of them have these super Earths. Are we special in having liquid water? On our surface? Yes. On our planet? No. Are we special in time? Maybe. The sun is a certain age, and the Earth is a certain age, and it takes a little while for life to arise. We know of other stars that are the same age as the sun, or even older. We have seen planets around these stars. Maybe they had life on them once. Maybe they did. Maybe they don't now. Maybe they never did. We don't know. We're just beginning to do this. This is by far my favorite picture of our planet ever taken. The Rosetta spacecraft, European Space Agency mission that went to the comet, 67P Churyumov-Gerasimenko, just rolls off the tongue. 67P, that the rubber ducky comet. You've seen a million pictures of this thing, right? It passed by the Earth and used our gravity to assist it to get to where it needed to go to visit the comet. And as it passed the Earth and went sort of on the other side of the Earth, so the Earth was between it and the sun, it got this beautiful crescent shot. And you can see that gorgeous blue color. This is a natural color image. What your eye would have seen if you had been there with it and you weren't, gasping for breath and dying. But that's what you would have seen. You see clouds here. You see that liquid water. You see that gaseous water. We don't know. We still don't know if there are any Earth-like planets out there. There are Earth-sized planets out there. There are planets that have, maybe Earth's temperature. There are lots and lots and lots of planets that have any one of these unique features that Earth has. But we don't know if they have all of them. And, does this make us unique? We don't know. For me, it does. Right now, it's the only Earth we have. It's the only Earth we know. It's the one we live on. It's our home. And so as far as I'm concerned, to answer the question, is Earth special? The answer is yes. Thank you very much. Okay, did I run horribly long? I have no idea. Okay. I'm willing to take questions if you're willing to hear my answers.
Oh, hi.
Hi.
I want to ask, has there been a time when during the transit method for a large planet, there's been some glimmer of a refraction, indicating an atmosphere on the edge of these?
Yeah. It turns out that in an exoplanet, especially these Jupiters, especially these hot Jupiters, when they pass in front of the planet, if they were solid, they would just block the star's light, and that would be it. But if they have a thick atmosphere, it's possible that some of that light from the star will pass through that atmosphere on its way to our telescopes. Atmospheres will absorb certain colors of light. For example, carbon dioxide is opaque to certain wavelengths of infrared. That's why we have a greenhouse effect. That's why carbon dioxide is a greenhouse gas. It traps, the Earth takes light from the sun, warms the planet up, the Earth turns around and emits thermal infrared light, but the carbon dioxide won't let it out. So if you were looking at the sun, you would see lots of thermal infrared light coming from the sun, but if you look at the Earth, there's not as much as you expect because it's being blocked by the carbon dioxide. So if some of that light from the star passes through the atmosphere of the planet, some of that light will get blocked. And so if you look at a star when the planet's not transiting, to give you a nice template, then look at it when the planet is transiting, and suddenly you see certain wavelengths of light are missing, and it's like, oh, that's hydrogen, that's helium, that's carbon dioxide. That can tell you what's in the atmosphere of the planet. That is a very, very difficult observation. That is right on the edge of what we can do. But it has been done. The James Webb Space Telescope, which will launch any decade now, I worked on it in 1996 when it was still on paper, literally on paper. We were drawing pictures of it to figure out what we were doing. But that'll launch hopefully in the next couple of years. That should be able to do that sort of method. It's much tougher for an Earth-like planet, but for these Jupiter-sized planets, it's a lot easier. And so yeah, you can detect them. And in fact, to go another step on this, I talked about these moons orbiting Jupiter. I should be clear that if there are moons orbiting these other planets, they may be habitable too. If you find a Jupiter-sized planet in the habitable zone of a star, it's a gas giant. You can't live there. But if it has big moons, then these moons might be able to have life on their surface because they're in the habitable zone of this planet. And we have not 100% sure discovered an exomoon yet, but there is one orbiting a planet that Kepler observed that appears to be a moon of a gas giant. It's a big moon. It's about the size of Neptune if it's real. There's astronomers right now working on it. I'm literally expecting them to make their announcement any week now. Their data is really, really close to being done. I'm hoping that they've actually discovered it. Be the first moon of a planet orbiting another star ever detected. But no reason not to expect that. There's even if you say there are 9 planets, 10 planets in our solar system, whatever, there are hundreds of moons. So moons outnumber planets by a huge number. And if Exoplanets exist, exomoons do too. And if they can be habitable, there could be trillions of habitable worlds in our galaxy. How about that? Sweet. Come on, one question. Anybody in Gaithersburg have a question? They might have to do sign language. I don't know if... Oh, here we go. Is it on?
Hello.
Oh, there you go.
Thank you. This was great.
Thanks.
So when I look up at the night sky, like how many of these stars have planets that we've looked at? You know, what kind of percentages are we talking about?
Right. That's the thing that stuns me. That these planets are so easy to find. And the thing is, the transit method depends on geometry. You have to have that orbit almost exactly edge on, because if it's tilted even a little bit and the planet's far enough out, it'll just miss the star from our point of view. So when you say, you know, we've looked at X number of planets, or X number of stars, 100,000 or whatever, and we found 1,000 planets, how many are we missing? And this leads up to the answer to your question. And it turns out a lot. You know, the majority are orbiting face on or at an angle, and we just don't see them. And depending on your numbers, you know, if you say 1 out of every 100 stars we find has a planet, but we're missing 90% of them, then suddenly your numbers become 1 in 10. Or something of that order. You know, it's not 1 in a million, and it's probably not every star, although, you know, we expect most stars have planets. But, you know, most stars have planets. And you look at our solar system, and there are 8, 9, 10, whatever planets. This means that even if your typical solar system is, let's just say 10, because that's a nice round number, and 1 out of every 10 stars has planets, that means there are many planets as there are stars in the Milky Way. And the Milky Way has, you know, 200 billion stars, something like that. And our galaxy is a big one, but this is telling you that on average, you know, there's 1 planet per star. And you look at all these other galaxies and you realize that there could be sextillions of planets in the universe. That's staggering. So when you go out and look up at the night sky and you see a few hundred stars, some of them will have planets. And in fact, there are naked eye stars that we have found that have planets orbiting them. And that to me is also amazing. These stars I grew up with, and now I can say, you know, I have a friend who does exoplanet research, and she has a table of exoplanets known, and she has crossed that with known planets in Star Trek, which makes me happy because that means there are bigger nerds out there than I am. And she has actually listed, you know, planets around. When Star Trek has mentioned the name of the star and the planet, then she can cross-check that. It turns out, there are quite a few Star Trek planets that are real, including Spock's homeworld, Vulcan. We have found a planet around 40 Eridani A, which is canonically Spock's star. So Vulcan exists, which I love. Yes, in Gaithersburg, from across the country.
Hi, thanks.
Hi.
So if we were to start considering life on methane system planets or moons, do we have any sense what that life might be like? If we're carbon-based, what would that be?
I don't know. You know, it could be carbon-based. It's hard to say. I mean, if you're in a sea of carbon-based molecules, can you have carbon-based life? I don't know. But life wants a liquid, because liquids are really good that if you throw a lot of glop in them, you can shake it up and that glop can interact. If it's just sitting on a rock, these two molecules, they're never going to meet. But if they're in a liquid floating around, they can get together and do what molecules do and be fruitful and multiply. So it may not be that it's important what the liquid is, unless it's corrosive or something like that. Liquid methane, you know, in the absence of oxygen, is fairly stable. If you have oxygen, it's fairly unstable. Yikes! That would be a very interesting thing to see through a telescope. Titan is on fire. But it could, you know, it's just that it would be a slower chemistry, right? It's much colder, so the chemical reactions may not happen as rapidly. But on the other hand, it may be more stable than water. I mean, water has a pretty wide temperature range that exists as a liquid. But if you're at the hot end, it can start to break things up. And so, maybe methane is even better at these cold temperatures. You can have even bigger molecules that can be more sophisticated. So it might even be better for life. I am totally making this up on the spot. I am an astronomer who studies how star explodes. This isn't even my field. I'm just an educated layman when it comes to exoplanets. A little bit more than that because I've studied some of the physics behind this. So I'm pulling this out of my hat. I'll say hat. But it's entirely possible that you could have life based on methane liquid, what that looks like, I don't know. Science fiction authors have written about that, and to add to that, I remember watching Star Trek as a kid and thinking, oh, you can't have planets around a binary system. That would never work. Or you can't have a green sky. Or you can't have this. You can't have that. And it turns out, yeah, you can have all those things. Every time we find a planet around a binary system, the headlines are always the same. Another Tatooine has been found. Like, okay, fine. Star Wars, it's okay. I mean, it's not Star Trek. It's okay. But it turns out, yeah, we find planets in systems that, you might have thought initially that could never be. And it turns out, no. We find planets orbiting one of the stars in a binary system, and we find them orbiting in big orbits around both of them. And it's just all these weird systems. There's this one called TRAPPIST-1 you may have heard of. It's a little red dwarf. It has 7 Earth-sized planets, all orbiting the star closer in than Mercury orbits the sun. 3 of those planets are in the habitable zone of that M-dwarf star. So, that system is something I thought is ridiculous. Having 2 planets that could both have civilizations. That was another thing in Star Trek where you have 2 warring civilizations. And it's like, yeah, I always thought that was silly. It turns out maybe not. I mean, the warring part maybe. But the idea of 2 planets that could support life in the same system, sure. No reason that couldn't exist. Life could be everywhere. Okay. Well, thank you all very much.